So today I'm going to talk about lenses, but before I do that, I'm going to give a quick overview and review of the ray model of light. Now, light obeys two different models. One is called the wave model, and one is called the ray model. The wave model is applicable when the wavelength is comparable to the size of object or opening through which the light is transversing. The ray model, on the other hand, is valid when the wavelength is very, very small compared to the aperture size, or the opening size, or the object with which the light is encountering. So since we're going to be looking at lenses being on the size of millimeters and centimeters, the ray model will be the appropriate model to use where we can neglect interference and diffraction effects due to light. And we only have to look at its ray-like properties. Now, what is a ray? When you think of a ray, you might think of a laser beam. Well, in reality, a laser beam, if it looks like a straight line of light, it's actually an infinite number of ray bundles. And an individual ray we could think of as being a laser beam, but having zero diameter or shrunk down to zero diameter. That would be a single ray of light. Any real ray that we observe is actually a bundle. Now, a ray is also an abstract concept. There's no physical thing such as a ray, but it's a useful model in that it tells us that light travels in straight lines between 2 points. And it's good for many practical optical purposes where we can neglect interference and diffraction effects. All right, so in review then, let's say we have a boundary between two different medium. Let's say that there's my line of boundary. I'm going to make that slightly darker. And on top of the boundary, I have an index of refraction N1. And on the bottom, I have an index of refraction N2. And the index of refraction N1 is equal to V1 over C. N2 is equal to V2 over C, where V1 is the speed of light in medium 1, and V2 is the speed of light in medium 2. So whenever light travels through a physical medium other than the vacuum, its speed is always slightly less than C, or at some fraction of C. So certain materials like acrylic, light can be traveling a fraction of its speed in the vacuum. Now let's say I have a ray of light which is incident on the surface or the boundary between the two mediums. This is my incident ray. And this incident ray comes in at an angle. I'm going to draw the normal line, and the angle I'll call theta 1. When this ray encounters this boundary, one of two things could happen. The light could either reflect, we could get a reflected ray, or it could refract. And this ray, which makes an angle theta 2 with respect to the normal, I'll call the refracted ray or the transmitted ray. Okay, now what determines how much of the ray is transmitted and how much is reflected? Well, in general, there is going to be a reflected ray and a transmitted ray. And this is described by something called the reflection coefficient and the transmission coefficient. So the reflection coefficient and the transmission coefficient, little r equals n2 minus n1 over n1 plus n2, and transmission t is equal to 2 n2 over n1 plus n2. So what you can see here from these two formulas is that the only time that there is no reflected ray is when n1 equals n2, which kind of makes sense because then medium 1 and medium 2, there's no optical difference in optical properties between the two materials, so there's no, in a sense, boundary or reason for the ray to reflect. But in general, unless the material is completely opaque, there's always going to be some transmission that takes place. All right, now how do we relate theta 1, theta 2, and theta 3? Well, these laws that relate these angles obey energy conservation and are in fact a consequence of boundary conditions of the electric fields governed by Maxwell's equations between the two interfaces. So what that actually works out to for our purposes is it works out to two basic laws which we have used: law of reflection and the law of refraction, sometimes called Snell's law. All right, now the law of reflection simply says the incident angle equals the reflected angle. Theta 1 equals theta 3. Now again, this is a consequence of boundary conditions pertaining to components, both parallel and perpendicular components of the electric field. And then the law of refraction involves indices of refraction. Sine n1 sine theta 1 equals n2 sine theta 2. So this allows us to, as soon as we know one angle, we can find any of the other two angles. The reflection and transmission coefficient will tell us how much of the ray reflects and how much of it refracts. Now, in this case right here, if theta 2 happens to be bigger than theta 1, that would mean I'm entering a material with a smaller index of refraction. But if the ray bends towards the normal as it enters into N2, that would mean I'm entering a material with higher index of refraction. Or in other words, the ray slows down, the ray being the direction of the flow of energy. All right. So I have theta 1, theta 2, and theta 3. Now, let me turn now to discuss lenses, because all lenses are going to do are apply the law of reflection and the law of refraction, and we're going to use these laws in order to produce an image by bending light when it enters into a transparent medium. It's going to bend on the surface of a lens. All right, so lens. Well, as you can imagine, there are many different kinds of lenses. And I'm going to define, because we could have various curvatures of lenses. Now, it turns out that spherical lenses never give us a perfect focus, but if we have a small enough cross-section, we can get pretty good focuses, especially when we combine multiple lenses together. So I'm going to define something called the lens plane. And on my lens plane, there is going to be a lens, which my lens will look something like this. I purposely am making each of these curvatures having a different radius. And the reason for this is because in general, you could make each side have a different curvature and just glue them together. But these are circular curvatures, just slices of a part of a sphere, you could think, of a transparent globe, let's say of acrylic, and you just slice off a little edge of it. So I'm going to call this curve right here, say it has radius R1, and this one has radius R2. I'm going to define the lens, something called the optical axis. Okay, the optical axis would be the line that basically bisects the lens here. Okay, now let's say I have an object over here, and our object is some kind of luminous source. Either it's producing light rays or it's reflecting light rays. Now those light rays, some of them are going to impinge on the lens itself. So here's one of the rays, impinges on the lens surface. Now you can imagine when it encounters that first curvature, Snell's law is going to give us a bending of the light. And I'll say that this lens has an index of refraction. N is the index of refraction of the lens. So there's going to be some bending. And then when it encounters this curvature, I have, once again, a normal line and the ray will bend again to this point right here. Now, the angles with which these bend are going to be governed by Snell's law. Right? I have to apply Snell's law twice on a curved surface because the normal line is going to be a function of how much that ray is below the optical axis. Okay, now you can imagine repeating this over and over again for a number of different rays. For instance, let's say I have another ray right here. Bends. It bends again. Let's say I have another ray up top here. Bends a little bit. Bends again. And these should be straighter than I've drawn them here. Or the rays should be straight themselves. They only bend at the surface itself. Okay, so it turns out that if you do the analysis, we get on the other side all of these rays converging at some point. And this is called the image. Now, this is what a lens does. It focuses the light rays to a particular point. Now, something interesting here is that this is mathematically, in your textbook, you'll see the derivation of of this result here, but I just want to point out that this result is approximate, and it only works for narrowly bunched rays. For instance, the farther it's something called the, we're going to use something called the thin lens approximation. Okay. All right. So putting all the results together, the only major result that we need here is called the lens maker's equation. And the lens maker equation allows us to find the focal length. Well, actually 1 over the focal length equals n minus 1 multiplied by 1 over r1 minus 1 over r2. Okay, so this result comes from Snell's law. It only works for, we could call this the thin lens approximation. Which is really a small angle approximation. And finally, r, which is the radius of curvature, we have to have a convention because it turns out r can be positive or negative. So r is positive. It's positive when the lens is convex towards the object. Okay, so finally, what is the focal? What is f right here? Well, that's the distance with which the rays become focused, and I'm going to come to that in a moment here. Okay, so convex is basically bulging towards the object. So in this example right here, R1, this side of the lens, since it's bulging towards my luminous source, my object, that would be a positive radius. R2, on the other hand, would be concave towards the object, so it would be a negative R2 if I was actually going to calculate the focal length of this lens. So you can see that for practical purposes, given that we understand this approximation right here, a craftsman, or this is why this equation was originally called the lens maker's equation, because this equation right here could be used to determine or to build a lens with any particular focal length that you wish. All right, now in an actual lens, you see that there are 2 points of refraction. Light bends there and there. In what follows, just for practical purposes, when we're sketching this, we're gonna sketch everything as if the refraction only happens along the lens plane, and we're gonna ignore the thickness of the plane. And again, this works really well for most practical purposes, but there are going to be, let's say, you have a really thick lens, or you're dealing with really small distances, or you have really large wavelength light, these approximations will break down. So let me talk first of all now, let's apply this to a converging lens. Well, a converging lens has a lens plane and an optical axis. This is just going to allow me to center everything on the picture. And a converging lens, the focal length turns out to always be positive. So I'm going to draw the lens kind of like this. It looks to be convex. So if I have a number of rays incoming, let's say from the left, So